Well, thank you, Roman, and everyone. I would like to start by saying that monitoring of CO2 stores, listening to Claudio, is really about securing conformance, um, or sorry, securing containment, establish conformance, and create confidence between multiple stakeholders. And that would include not only the developer and the regulator, but also the public. So those are the three key stakeholders that you need to make sure are aligned when you plan for monitoring of a CO2 store. In that perspective, there's a dualism, of course, meaning that the developer would try to minimize the monitoring setup in order to bring costs down, whereas the regulator on their side will try to maximize the monitoring setup in order to make sure that they can really stand behind the permit application as it is filed. And the public is in between, and they don't really know who to trust. So that's the big issue. So what I'm going to talk about now is some results that we had from the ACT2 Digimon project, but I will also pass this over into the new CATP Romanco project so that you can see the line here. So starting with the Digimon project, let's see now, where is the down button here? The Digimon project was really about looking at how different technologies for monitoring of CO2 stores, low cost, low resolution, high cost, high resolution, could be combined to address the different aspects of monitoring of CO2 stores. So be it saturation, pressure, or other parameters related to CO2 stores. And we were particularly concerned with distributed sensing techniques like fiber optics for acoustic measurements, but also for chemical sensing. So the Digimon project had a lot of attention to the DOS systems and how to improve these. And we actually focused on both on monitoring of the CO2 plume itself, um, well integrity, as well as the overburden, realizing that failure of a CO2 store, it's not a failure in the sense that the CO2 is leaking directly to surface or to the seafloor, but that failure is related to breach in one or several barriers that you have to protect your CO2 stores. So what we did in the project was to organize the project into three different work packages. One dealt with critical technology elements, the system components, if you like. And the second work package was about integrating these components into a holistic systems. How can you combine fiber optics with seismic sensors, with gravimetry, and blah, blah. And the third package was about the social acceptance part of monitoring. How do you make sure that the system you apply and design is also acceptable from a societal point of view? We had some targets that we defined that relates to these ambitions I was just referring to. One was to increase the TRL of individual components of the system. The second was to optimize and validate processing software for system components. Third, develop an effective DOS data interpretation workflow. Four, develop a cost-efficient integrated monitoring system. Five, produce a flexible system compliant with prevailing and emerging standard data and also standard communication platforms. And six, to develop a societally relevant and acceptable monitoring system. And we managed really to deliver on most of these targets. I think where we did not manage to completely deliver as we had planned was on the system or at the system level, be it target 4 and 5. We were able to demonstrate the individual component at the component level, but we failed really to be able to demonstrate this at a more holistic field scale and pilot scale. So now I'm going to show you some individual results. From the VP1, we carried out some field tests. First of all, we had a data set that we received from the Antarctic, which was not part of this, but were we had access to the data. We also performed a field test in the field research station in Alberta in Canada, and we had also a test in Svelvik in Norway. And the key output really of these tests was to enable us to improve the DOS processing algorithms and also algorithms to acquire and process gravity and deformation data, methodologies for ambient noise interferometry, as well as feasibility of using distributed chemical sensing tools for CO2 leakage monitoring. In the VP2, this was a lot to do with how we integrated, as I said, the system components. So we performed a technology readiness assessment of all the system components. And we set up an inversion framework for a case study at Smeaheia offshore Norway that included conventional seismic DOS, 4D gravity, and seafloor deformation data. And the output of this was that we had an assessment study, a report that addressed all these system components. We developed a framework for forward modeling for the case study, and also a framework for the inversion part, where we actually the scenarios Meaheia and inverted the DOS and the seismic data, as well as gravity. Then the third work package, we inherited, or we made use of a technology for addressing societal embeddedness or societal acceptance that was developed by TNO in the Netherlands, who was partner with this project, and we used this methodology to address concerns of monitoring and CCS also on a larger scale. And the good thing about this was that we were able to take this methodology for societal acceptance or societal embeddedness, and we aligned that with the technology readiness level. So on a scale, the technology readiness from 1 to 7 or 1 to 9, whatever you use, we had a SCL scale from 1 to 4 that were directly aligned with the technology readiness level scale, which enables you to actually monitor how mature is a project, not only from a technical point of view, but also from a societal point of view, which is kind of critical. If you think about the three stakeholders I referred to in the beginning. And then I will jump over to this new Romanco project, which is about advancing state of the art, where we try to build on the results that we had from the Digimon project and carry this over into this new Romanco project. So for this project, the overall objective is to develop a multidimensional and robust performance assessment methodology, and advanced risk-based monitoring and societal implementation strategies. And we address three research frontiers in this project. Number one, field scale application of multiphysics data modeling and inversion. Second, risk governance strategies for CCS. Third, multidimensional decision support. And you can see the partners at the lower part. So about multiphysics inversion, in order to mature multiphysics inversion from the TRL 4 to 5, which is where we were in the Digimon project, to a TRL 6, which is the ambition of this project, we will work on some key challenges. One is to extend the inversion framework from the 2D data, a limited data set that we used in Digimon, to field scale, 3D, which is a very complex challenge, I would say. Not only will it call for development of the algorithms that we use for inversion, but also it requires much higher computing power resources. So we need access to high power computing platforms, and there's a lot of things there that we have discussed between the partners how to proceed. So and then we move to the second, the societal risk assessment. In the Digimon project, we kind of looked at the methodology to actually monitor or actually assess a risk assessment using this SEL methodology. In this project, we want to bring this methodology into the industry risk assessment methodologies. And Claudio, in his presentation, was showing how for Quest they use the bow tie risk assessment methodology. What he didn't say was that the bow tie risk assessment methodology used as a standard in the industry covers basically technical and economic aspects. We don't have methodologies how to address public societal concerns in such risk methodology. So in this project, we have one of the key companies um, which offers risk assessment studies for industry today, RiskTech, and they will be involved in this project. And what we will try to do is to develop a methodology how to address societal concerns and bring this into standard industry-based risk assessment methodology. And then finally, we plan to um, address multidimensional decision support from the perspective that neither the operator, developer, or regulator today have kind of standard best practices that you can refer to and that you can use as guidelines for new projects. So for this project, we intend to develop a methodology based on the value of information concept, which is a concept that enables you to look at a new methodology, how well that methodology addresses the concern that you have for what cost, basically. So in this new project, we will design a probabilistic methodology that will enable regulators and operators to assess the expected performance of monitoring strategies. And there will be one static part that enables you to go into a project upfront before or in the planning phase. And there will also be one part that addresses the dynamic behavior of a reservoir as operation is launched. Thank you for your attention.